Okay, so when you think about a 3D printed object, you probably think about its shape, right? But what if I told you the most valuable part of an advanced 3D print isn't what you see on the outside, but a secret that's literally baked into its very structure? Today, we're going to pull off a little high-tech heist and see exactly how AI can steal that secret. So on the left, you see the design. It's just a simple, perfect 6 mm cube. But on the right, that's the reality. It's not some solid block of plastic. It's actually a super complex stack of intricate layers. And it's inside that structure, in those layers, that the secret blueprint is hiding. Looks like a simple box, but really, it's a puzzle. So what is this secret we're trying to get our hands on? It's not the shape of the object. I mean, anyone can scan that. The real prize, the crown jewel, is the hidden how, the exact recipe for how the materials were laid down layer by tiny layer. And that how has a name. It's called the toolpath. It is the literal set of instructions the 3D printer's nozzle followed. For these high-tech composite materials, the toolpath is everything. It's what gives the object its strength, its flexibility, its unique properties, all the stuff that makes it so valuable. And of course, that makes the toolpath a huge target for industrial espionage.
Now to get that toolpath, we've got to look inside the cube. But we can't just crack it open. That would completely destroy the evidence. So instead, our investigators are going to perform what you could call a digital autopsy. The main tool for this job is a microcomputed tomography scanner, or a mu-CT scanner. Just think of it like a crazy powerful medical CT scan, but for objects. It takes thousands of X-ray images and digitally stacks them up to build a complete 3D model. We can explore every nook and cranny inside, layer by layer, all without leaving a single scratch.
And here is what that scanner sees inside just one of those layers. Those little white lines, those are tiny glass fibers mixed into the plastic. Now, notice how in this slice they are all lined up perfectly horizontal, at a 0-degree angle. This is our first huge clue. It's like a fingerprint left behind by the printer. But then, check this out. In the very next layer, the whole pattern changes. Now the fibers are all lined up vertically, at 90 degrees. This is the proof. The printer was deliberately alternating its path with each layer, probably to build strength. So we found the pattern, but trying to track this by hand across hundreds of layers? Forget it. It'd be impossible. So to crack this incredibly complex code across the entire object, we need a special kind of partner, one that can spot patterns in an instant and, never gets tired. We need an AI detective. The specific AI for this job is something called a recurrent neural network, or RNN. What makes an RNN so perfect here is its memory. See, unlike other AIs that might look at each image on its own, an RNN actually remembers the image that came before it. It gets sequences, so it understands that the angle of layer 50 might have something to do with the angle of layer 49. It's basically built to solve this exact kind of layer-by-layer mystery. But even the most brilliant detective needs to go through training. The researchers started with 433 really clear scan images, where the fiber direction was super obvious. Then, they used software to rotate each and every one of those images 1 degree at a time, all the way from 0 to 180 degrees. And just like that, they created a massive library of examples for the AI to study. And when I say massive, I mean it. This whole process, which is called image augmentation, turned their 433 starting images into over 78,000 unique training photos. That, my friends, is how you turn a rookie AI into a world-class expert on fiber orientation. They also had to prep the evidence, right? The image on the left is what the scanner sees. Kind of noisy. The one on the right is what the AI gets to see. They've processed it to clean up all that visual noise and make the fibers, the key clues, really stand out. It's like a detective using a special filter to make fingerprints just pop. All right, so after hours of intense training, our AI detective was finally ready. It analyzed all the scans from our mystery cube, layer by layer, predicting the toolpath. So the big question is, how did it do? Well, the results were absolutely staggering. The AI's accuracy was measured by what's called mean square error, which is basically a score of how far off its guesses were. The closer you get to 0, the better. And our AI? It scored a 0.04. To put that in perspective, that is an incredibly small error. Our AI detective wasn't just good, it was nearly flawless. And here, right here, is the visual proof. The blue dots you see, that's the actual correct fiber angle for each layer. And that orange line, that is what our AI predicted. I mean, just look at how closely they match up. It is almost a perfect one-to-one overlay. This is that moment where the case was totally cracked. The AI could basically read the printer's mind. See, once you can predict the fiber angle for every single layer with that kind of accuracy, you have everything you need to rebuild the original G-code. And G-code is the master file. It's the exact set of instructions the printer follows. With that in hand, well, the secret blueprint wasn't a secret anymore. So, what do you do once you've managed to steal the digital soul of an object? You create a copy, of course. And this is where the story takes a really fascinating and frankly kind of unnerving turn. Using that stolen G-code, the researchers printed a replica. And let's just look at the tail of the tape here. The original's length was 6.08 millimeters, the copy 6.10, the width 6.13 versus 6.15, the height 6.07 versus 6.09. We are talking about differences of just a few hundredths of a millimeter. The average dimensional difference between the original and the replica was just 0.33%. This wasn't just a good copy, this was a near-perfect counterfeit, totally indistinguishable from the original without some highly specialized lab equipment. So why does this matter? This goes way beyond one little cube. This technique is a serious threat to intellectual property for any industry using advanced 3D printing. We're talking aerospace, medical implants, you name it. It just flings the door wide open for high-quality counterfeiting and creates all these new cybersecurity challenges. I mean, how do you protect a blueprint that's physically embedded in every single object you make? And that really just leaves us with this one final kind of mind-bending question. As our ability to scan, to decode, and to replicate gets this powerful, we have to ask, in a world where a copy can be a perfect physical and digital twin of the original, what does the word authentic even mean anymore?